we had gotten up to about this point right here. All right. In modeling linear functions, you have already discovered that for x values that are evenly spaced, the differences between the corresponding y values must be the same. That was the slope or the rate of change. With second and third degree polynomials, the differences between the corresponding values are not the same. However, finding the differences produces an interesting pattern. So when you look at a first degree polynomial, this one here, notice the common difference is 3, and so it was 3x, the slope. Well, with a quadratic, y equals 2x squared minus 5x minus 7. If I do the first set of differences, they're not the same. But if I take the differences of the first differences, so I call it the second difference, if it's second degree, their second difference will be constant. It'll be the same. In a third degree, guess what happens? I do the first difference, the second difference, and then it's the third difference. So this is a process called finite differences. So when you do finite differences, it will actually tell you the degree of your polynomial, if it is a polynomial. So let's look at this example 1. It says find a polynomial function that models a relationship between the number of sides, S, and the number of diagonals, D, of a convex polygon. So what I want you to notice is in a triangle, there are no diagonals. Okay, so we would put 0. In a quadrilateral, do you see that there are 2 diagonals? What I want you to do is I want you to count for the pentagon how many diagonals, and I find it easy if you use your pen and you draw them, you'll be able to count how many there are. And then do the hexagon. Then I want you to figure out how many would be in a dodecagon if you follow the pattern. Okay, so right now I want you to find out how many diagonals are in the pentagon, how many diagonals are in a hexagon that are drawn, then kind of continue the pattern until you see you would get 12-sided polygon, which is called a dodecagon. All right, Jake, how many diagonals did you get for the pentagon? 5. And DP, what did you get for the hexagon, 6 sides?
8.
You got 8. Did everybody agree?
Yeah,
I got 9 as well. Okay, there's 9. All right, so do you see that this increased by 2, increased by 3, increased by 4? So let's try to follow a pattern here because we've got to get up to 12. So, Gabe, if I follow this pattern, what would be the number of diagonals for a 7-sided? 14. All right, so then William, if we keep going, how many diagonals would be for an 8-sided? 20. All right, let's keep going here. And then Nick, if I went to 9, well, how many would I have there? 27. All right, and Brennan, if I go to 10, how many would that be?
Wouldn't it be plus 8, so 34.
27 plus 8. 35. All right, Avery, if I went to 11, how many would that be? 44. And then Matthew, if this continues, how many diagonals would the dodecagon have? We're at 44 and we're gonna add 10.
Oh,
54. There we go. Okay. So what I want you to see is this is what we call the first difference. They're not the same. But watch this. If I take the difference of those differences, do you see that they are all, in fact, 1? So I should be able to come up with a quadratic function. And I'm going to show you how we do that. So what you're going to do, if I want to write a quadratic function, all I need are 3 points on the parabola. So watch what I'm going to do. This is going to be so cool. And so we're going to circle back to our very first unit this year. So if I take the point 3, 0, and I'm using y equals ax squared plus bx plus c, does anybody know where I'm headed? Cal, I think you know. Where am I headed?
I don't know.
Yes, it's a system of equations. I saw you recognized. You're like, okay, I think I know. So then I'm going to try 4, 2. Does anybody know where 3, 0 and 4, 2 are coming from?
No.
Gabe? It's the table. It's the table above, okay? In the table above are the points. I'm trying to come up with a formula that I could find the number of diagonals of any convex polygon I want to. So we're going to do 2 equals a times 4 squared plus b times 4 plus c. So Elise, what would be another point that I could come up with then? Yeah, 5, 5. I'm just going from my table above. Now, one way to solve this system is by hand, okay? I could do this by hand, and I could multiply like the top row by -1 and add it to the second row, and that would get rid of C. And I could multiply the second row by -1 and add it to the third row and get rid of C. But we had another way we could do a 3 by 3, and that's why I asked you to get your calculators out. What could we do instead? Matrices. Okay, so let's do that. So we're going to put 9, 3, 1, 16, 4, 1, 25, 5, 1. And you do need to write out the matrix equation like this. So this is my A times X equals B. And what we're actually doing, once you get this entered, Once you get your A matrix in, your B matrix in, you can do A inverse times B. So hopefully you remember how to do this. But part of your work, and we're gonna have a quiz on Friday, okay? We're gonna have a quiz Friday. Today, we're finishing up 6.1. Tuesday, Wednesday, we're gonna do 6.2, and Thursday, we'll review. But make sure, and you will see a problem like this on the quiz, where I give you 3 points and ask you to come up with the quadratic model. You're gonna write, this is the type of work I'm expecting to see.
So what you do is you click new matrix, and this needs to be a 3 by 3, so you enter it, okay?
And then I can help you, just so you get your answers out. Now, when you get this is not my final answer, okay? This is not my final answer. This is what does this tell me? What does this answer matrix actually tell us? Like, what were we doing? Yeah, Hannah?
Finding the x values for A, B, and C.
Good job, okay? It's telling us the values of the A, B, and C in general form. So this is y equals 0.5x squared. Whoops, I'm going to go ahead and make that a minus 1.5x plus 0. Now you're not going to leave a plus 0. We'll tidy that one up. So hopefully you remember how to use your calculators. All right, questions on that? Now, I'm probably not going to ask you higher than quadratic. Like if it's linear, then that's giving you the slope. Okay, that first difference is the m and y equals mx plus b. And you just have to take 2 points and find the y-intercept, okay? We'll do one more of these in the closing task, but like I could ask you just what's the degree, and it could go out to the third or the fourth difference, and it's a third, a cubic or a quartic, and so on. All right, so here's a closing task to kind of wrap up the lesson. I'm going to pause a moment and give you maybe 3 or 4 minutes. Determine if each equation is a polynomial. For those that are polynomials, you're going to finish the rest of the table. If it's a no, you stop, just like in the beginning part of the 6-1 homework. For those that are polynomials, state the degree and the leading coefficient. The leading coefficient, again, is the number in front of the highest power, the term that's giving you the degree, okay? So go ahead and fill in your box. And then start number 2. I do want to sort of guide you through that one since we only did one example of finite differences. right, letter A. Matthew, is this one a polynomial? Yes or no?
No.
What made you say no?
Because there's 3 terms, and you combined all like terms.
Okay, so if you look at letter A, if I multiply this out, I would get 10x squared minus 2x plus 15x minus 3, which you should definitely try to put it in general form. So isn't this a yes? Yeah, this is actually a yes. Okay, so and I'm glad to have this conversation. If it's not in general form, try and put it in general form before you decide. Okay, so that's excellent. Okay, this is excellent for us to come across. So then, Max, what's the degree? 2. And then, Liam, what is the leading coefficient? What's the number in front of the highest powered term? 10. Okay. And then, Brennan, what's the constant term?
-3.
-3. Okay. If we wanted to name this, even though you weren't asked, it's got 3 terms, and the highest power is a 2. So, William, what would we call this, even though I wasn't asked?
I wasn't here Friday. I don't really know what those names are.
Oh, okay. Well, if you have 1 term, it's a monomial. 2 terms is a binomial. 3 terms is a trinomial.
Trinomial.
Yeah, it's a trinomial. And then do you remember from our chapter 5, when you have x squared, that's quadratic. So this would be called a quadratic trinomial. All right, letter B. Drew, do you think this is a polynomial? No, it's not. And let's go ahead, in case you're asked this on the quiz Friday. Why is this one not? Yeah, DP?
Negative exponent.
Good job. The negative exponent. Polynomials. Okay, here's the big idea that we want to review. Polynomials have exponents that are whole numbers. And whole numbers can be 0, 1, 2, 3, and so on. They cannot be negatives, and what else can't they be? Decimals or fractions, okay? Good job. All right, now letter C is tricky. Who wants to try this one? Is this a polynomial? Yes. What's the degree?
0.
Woo! Okay, this is awesome, because this is really when you have a constant, and this circles back to the table talk. And you remember when I asked Avery, okay, what's an example? And she said, well, any number, any like real number, and she chose 3. Pi is a number. 3.14, yes, it's irrational, but it's still a constant. So the degree is 0. Now this one's tricky. What's the leading coefficient? It's not 1. It's pi, okay, because this is the weird case that the constant is the leading coefficient. Okay, that's the exception. All right, letter D. Is this a polynomial? Yes or no, everybody?
Yes.
Yes. What's the degree? 3. Now this one's not in the right form. So I personally like to pause and put it in general or standard form. It depends on your textbook whether they call it general or standard. All right, now that I have it in the right form, what's the leading coefficient? -25, and what's the constant? -90. All right, give me thumbs up, out, or down. How do we feel about naming, degree, coefficients? Okay, so we've got 3 more days to get it ironed out, okay? All right, number 2. It says find the equation of the polynomial function that models the data at the right. So this is what we call the finite difference method. So here's what you're going to do. in order to do your differences, you take the second y value minus the first y value. And I'm going to call this column D1. So 2 minus -1 is 3. 7 minus 2 is 5. 14 minus 7 is 7. 23 minus 14 is 9. 34 minus 23 is 11. And 47 minus 34 is 13. I'm going to pause a moment so they're not the same. If the numbers had all been the same, it would have been linear or first degree. Now you're going to do the second set of differences. Now we need to be really, really careful because these all end up being positive. If the second number is smaller than the first y value, then that's a negative difference. Does that make sense? Okay. So this is 2, 2, 2, 2. So it isn't because the difference is a 2. Okay, I don't want to mislead you. This was probably maybe a bad example. It's not because the difference is a 2. It's because the differences are all the same. Okay, so this is second degree or quadratic. Then you pick any 3 points. I typically just pick the first 3. If it's quadratic, general form is y equals ax squared plus bx plus c. So look back at your notes. I want to give you like a 2 or 3 minute head start on me. And I want to see if you can write the system. You're plugging in that x is 0 and y is -1. Come up with an equation. Then you plug in x is 1 and y is 2. You get an equation. Your system should have A, B, and C. If you're struggling a little bit with that first row, you really do want 0a plus 0b plus 1c so that you know what to put into your matrix, okay? I know that's a little confusing when the x value is 0. For those of you that have gotten this far, did you get an answer matrix of 1 to -1?
Yeah.
Now that's not our answer. This is going to be one of the trickiest parts here. What I found is the coefficients A, B, and C. So I'm going to get y equals 1x squared plus 2x minus 1. Now you could put the 1 in front of x squared or leave it x squared.